All right, this is Jack Jackson. In this video, we're going to look at isosceles trapezoid. By the way, it's important we study parallelograms before turning our attention to isosceles trapezoids because we're going to be using some properties of parallelograms and the proofs of the properties of isosceles trapezoid. So by definition, a trapezoid ABCD is an isosceles trapezoid if and only if it has at least one pair of congruent base angles. Notice it doesn't say anything about the legs being congruent. We'll actually prove that. Okay. Um, a parallelogram also has a pair of of legs that are congruent. It's a trapezoid with a pair of legs congruent, as is an isosceles trapezoid. But these two things have very distinct properties. Okay. Note the proof first requires you to establish properties of Euclidean parallelograms from the previous section, so it's important that you study parallelograms before studying isosceles trapezoids. And so if any of you are ever teaching this to secondary students, remember the order there matters. There are no trapezoids and hence no isosceles trapezoids in spherical geometry, but because of the existence of so many different parallel lines in hyperbolic geometry, the class of isosceles trapezoids is more general than the class of isosceles in hyperbolic geometry. It's more general than the class of isosceles trapezoids in Euclidean geometry. An isosceles trapezoid in hyperbolic geometry does not have any of the cool properties of the following theorem other than the defining properties. However, in hyperbolic geometry, if we restrict the class to be isosceles trapezoids with a pair of congruent legs, then that class has most of the same properties shared by Euclidean isosceles trapezoids. The main thing to notice, the following theorem is for Euclidean only. So if you're just studying Euclidean, cool, we're just doing Euclidean geometry here. Now here's a task that you should do yourself. Okay, it's an investigation in GeoGebra for Euclidean isosceles triangles. So you can do this doing the basic tools in Euclidean geometry. So I'm going to ask that you do this yourself before going on. If you're doing it yourself, you can learn a whole lot more than if you just follow what I'm doing here. So start by constructing a general trapezoid, a general isosceles trapezoid. And here's how we can do that. So you should have three free points, A, B, and C, which will be the vertices of the isosceles trapezoid ABCD. So then construct sides AB and BC. And now we have three vertices and the two sides of the desired trapezoid, isosceles trapezoid. By definition, we need side BD to be parallel to side AB. So make the unique parallel line L through C parallel to AB. Point D is going to be on this line, but it's going to be a specific point. Okay. Measure angle ABC. That's going to be an interior angle of our quadrilateral. Rotate point A about B through the same measure of this angle in the direction so that ray AB prime intersects line L. The intersection is point D. Complete the other sides and hide everything except the sides and the vertices. And this will make the control points the vertices A, B, and C, and quadrilateral ABC D will always be an isosceles trapezoid, and you should be able to get all possible isosceles trapezoids out of that. All right, so now that you've done that, do that first. Then you want to do these tasks sort of one at a time. So you may want to just do each task, press pause on the video, do the task, come back, look at the next task, press pause, do it, and so forth. Okay, so the next task is once you've got your general isosceles trapezoid, measure the pair of base angles at A and B. Now they should be congruent, as we made them that way. Now measure the other pair of base angles at C and D. What do you notice about them? Test your conjecture and then prove it. This doesn't require any extra constructions. Okay, see if you can do that and then come back. Press pause now. All right, hopefully you've done tasks 1 and 2. Now measure the sides. What do you notice? Test your conjecture. We'll prove it in a bit. Press pause now. Okay, of course, what you should have found there is that the legs are congruent, but we're just going to take us a little bit to prove that. So now arrange it so at least temporarily AB is greater than CD. So side AB is the longest side. Now construct the line through C parallel to side AD. Now it's going to have an intersection with side AB. Let's call that E. Okay. What kind of quadrilateral is quadrilateral ABCD? Okay, so just sort of test that out, make sure it works. You want to keep the AB the longest side for this to not break. It's a parallelogram, right? So use the properties of parallelograms, which again must have been studied first, to prove that AD equals AC or CE. Now, what kind of triangle is triangle BCE? Test and prove this conjecture. All right, so now you've got something that's interesting. Use the results of what you just did in 6 to prove part 3. So if you haven't done this yourself, stop now and sort of get caught up, do these different things. All right, now you can actually get rid of that parallel line if you want, now that you've done this. Now construct both diagonals, measure their lengths, make a conjecture about the lengths, test them, and then prove it. And the hint here is you should be able to prove that you have a pair of congruent triangles. Okay, see if you can do this yourself. So do this yourself before you go on any further in this video. Okay, press pause now. Okay, now I'm assuming you've already done this yourself, but I'm going to show you how this plays out. Okay, it's much better if you do it yourself. Here I've done some of it, but I'll start over. So this is just a basic GeoGebra place. I'm going to start by taking this and making A, B, and C. So these are free points. They can go anywhere. Okay. Now, point D's got to be on the line. It's got to be a trapezoid. It's got to be, this CD has got to be parallel to this line. So let's make a unique parallel line through C parallel to this line. Okay, so D's got to be on there. Now, where else could D be? Well, we know that this angle here should be the same size as the angle over here. So let's measure this angle here. So we're going to measure angle CBA. And just to be sure, let's go ahead and make sure that that is between 0 and 180 degrees. And we'll show its value, but there it is in radians. You can switch it to degrees if you'd rather. Okay, so we have that. So now, we want to probably name this something rather than a Greek letter. Let's rename it, just say A, lowercase a. Okay, so now, actually probably it's angle B, so maybe it may make more sense to rename it B. All right, so now what we want to do is make sure the angle at A is the same as size as this angle at B. So one way we could do it is by rotation. There's another way up here, but let's do it with the rotation way. So I'm going to click on rotate B about A through an angle of size A, and we want to go in the counterclockwise way. That's good. No, that's not what we want. Something was not right here. Oh, it's angle B, not angle A. Gotcha. Okay, so we want to do rotate B about A through angle B. Yeah, that worked. Can't see it right now, but B prime's up here somewhere. Well, did it work or not? Let's see here. Let me try that again. Something didn't seem to work right. Rotate A about B through angle B, and we want to go counterclockwise. Where did it go? Okay, so let's see if we can do, let me try again. Okay, I restarted it and got it to work. I'm not sure what was happening there, but it's working now. So that gives us there. Now make this ray going from A through B prime. And then we want to find that intersection point right there, and that's our D. So now we could hide these things if we want. I'm going to just leave them there, but I want to make them first of all, I want to make them a light gray color, and that's probably good enough. And then we're going to finish out the remaining line segments here and here. So now we notice that that line segment and that line segment are parallel. We can mark them as being parallel with arrows. And then we want to look at these segments here. Okay, so the next thing I ask you to do is measure this angle down here. Now, if we did this correctly, this angle here, okay, should be the same size as this one right here. Yeah, looks like it. Okay. Yep, it's working, including you can get a right angle. You can mess it up by making it not simple, but okay, if it's coming down here, that's not going the right direction. So it's not perfect, but it gets us all the different trapezoids here. Okay, so we do have a isosceles trapezoid. Now what we want to do is measure the other angles here, here, and here. And let's take both of those. And let's just get the value, 0 and 180 degrees, and let's make them red, let's say. What do you notice about them? Hey, they're congruent as well, right? So if these are congruent down here, these are congruent up there as well. So if you get one pair of congruent base angles, you get the other. Can we prove that? Yeah, we can. Since this is a trapezoid, we know that a pair of consecutive angles that are not base angles have to be supplementary. So you know that one and that one are supplementary, and the angle at B and C are supplementary. Well, since these two are congruent, this one is going to, C is going to be supplementary to this. So we opposite supplementary angles, and that's going to make these two congruent as well. So if you get one pair of base angles congruent, you're going to get the other pair of base angles congruent true on a trapezoid. All right, so we have some congruent angles there. That's cool. All right, now the next thing I ask you to do is make sure that AB was the longer side, at least for the moment. And then we want to take point C and make the unique parallel line through C parallel to this side AD. Now notice it's going to intersect right here at one single point, and I said call it E. So by definition, we have a parallelogram. Well, one thing we know about a parallelogram is this side right here. Let's see if I get it. Yeah, that side there is congruent to this side right here. So those are congruent. Okay. Now, what else do we know? Well, we know these are parallel lines here, this line and this line. And so we know that corresponding angles are congruent. So that means that this angle right here, we've proved, is congruent to the one over here at A. See? Same size. Well, wait a minute. These two angles are congruent. So what kind of triangle do we have here? CEB. Oh, wait a minute. That is a triangle with a pair of congruent base angles. Has to be what? An isosceles triangle. So it also is congruent as well. So what do we just prove? We prove that the legs are congruent. Okay? So legs congruent wasn't part of the definition, but it was something we could prove. All right, let me just go ahead and get rid of that for now. But now we know the legs are congruent. Next, we want to go and make some diagonals. In this case, I want both of them. And let's measure the lengths there of that diagonal and that diagonal, which I can just do by saying, put a value on that. That's the measuring the length. What do you notice about those two lengths? So that one and that one turn out to be, I like them green. Those turn out to be congruent to each other. Now we can't, well, let's not mark it yet because we haven't proved it. Okay, so what do we have? Well, we do have some sides here that are congruent. We've got this triangle here. I'm going to mark the interior of it so we can keep, so the triangle A, D, B, that triangle. And I want to compare it to this triangle, B, C, A. Okay, let's give it a different color. Okay, so we got two different triangles there. Can kind of marking their interiors may help. Well, what do we have that we know? Well, we know that the angle A inside this triangle, ADB, so that's the angle BAD, and this angle here at B are congruent. That's the angle, so if I call this a BAD, the corresponding way would be ABC. Those two angles are congruent. And we already have just proved these sides are congruent, so it's important we did that next. And the base down here is congruent to itself. That's a side both of them have. So is that enough to make the triangles congruent? Sure is. That is by side, angle, side. We have those two triangles congruent. So that's enough to show that those are congruent triangles. Okay. And that makes what? It makes the diagonals congruent. That's interesting. Okay. Now, what we also get is we get two smaller congruent triangles. ADE and BCE are also congruent. They've got a pair of congruent vertical angles here. And remember, since we just proved that the two bigger triangles were congruent, that's ADB versus BDA, we have this angle. Let me go ahead and mark it. Let me get rid of that one for now and mark these angles. So we should just prove that these angles are congruent. This one at ADB versus BCA. Okay, so we want both of those angles to be between 0 and 180 degrees, and let's just give them a different, let's make them orange. And just to show this value is good enough. Look at that, they're congruent to each other. See, we just proved that. Okay, so we have that. We have a side here, and then of course we have vertical angles here. A pair of vertical angles are going to always be congruent, like D, E, A, that one, and here. So those two angles right there like, whoa, that's fine. It's not what I meant to do though. I meant to get this guy and that one. So those are congruent to each other, there and there. Okay. So those are congruent, and they're vertical angles, so that's nothing fancy to prove there. We know that's for sure. So now what do we have? We have, let's see, we have those angles are congruent, these angles are congruent, and we already have these sides over here. So we have angle, angle, side. These two triangles are congruent. So that means, of course, that the distance from A to E is the same it is from B to E. Okay. What else can we show? Well, these two triangles at the top and bottom are definitely not congruent, but we do get the Z property tells us that this angle is congruent to the angle here, DAC. Okay. I'm sorry, DCA is congruent to BAC. So this angle right here is congruent to one up here, and this one's congruent to the one up there. In fact, these are both isosceles triangles. And they're similar. They've got all the angles the same size, corresponding angles measures are the same, but they're proportional in size. We could even try to figure out what that proportionality constant is. It may actually depend on where we put. For example, they could actually be congruent if it's a rectangle, or they could be, it could be quite a bit shorter. Okay. So we get some interesting things there about the trapezoid. Okay, and we could prove all those things. The order we end up going about proving some of these things is kind of important. Let's see what else we could prove. Yeah, I think that's most of what we want to do, at least at this point. So here are some of the properties that we just found for us and proved for an isosceles trapezoid theorem. An isosceles trapezoid, now this one I named it a little bit differently. Isosceles trapezoid STUV with bases ST and UV, and angle S is congruent to angle T. That's an isosceles trapezoid by definition, has the following properties. The bases are parallel, that's part of the definition. The legs are congruent, we had to prove that. And we couldn't prove it directly, we had to prove some other things first. Both pairs of base angles are congruent. We proved that early on. Any non-pair of base angles are supplementary. That was one of the first things we did. Opposite angles are supplementary. We did those things about the angles without doing any constructions. Triangle SUV and triangle TVU are congruent. It's cyclic, which we have not proved, meaning you can draw a circle around the whole thing and hit all the, there's possible to draw a circle so that it hits all the vertices. We have not proved that, but it is true. Triangle VSY is congruent to triangle UTY. Triangle VYU is congruent, and triangle SYT are similar isosceles triangles and has reflective symmetry about a line containing the midpoints of the bases. So we did most of that already. Okay, now here's the basic order that we did, the outline. Show the other pair of base angles are congruent. Use the parallel postulate to draw an additional line segment forming a parallelogram, and use it and the isosceles triangle theorem to show the legs are congruent. Then draw the diagonals. Got to do that first. Then draw the diagonals to show the two larger congruent triangles. Next, look at the four triangles you get with looking at the two diagonals in the sides, and show that two of them are congruent and the other two are similar, isosceles. Okay, and here is the proof written out. I'll just leave it up here on the screen for a minute if you want to pause the video and take a look at it. But we actually did all of this already. Okay, so I'm going to go on. There we go. This is the part about the midpoints of the bases and proving that part. So I'm just going to leave that up there and let you take a look at that. Also, I have my big classification of quadrilaterals, and we look at number of parallel sides. Here's an isosceles trapezoid. There it is. There's the altitude or height if we want to draw that in. Here's the midline. Here's our line of symmetry. Here's the related parallelogram. And there's the circumscribed circle that is always going to be there that we mentioned. This one is constructed a little bit differently than the other one so that this midpoint is a control point. But it does allow, I think it allows, yeah, it allows it to be a rectangle. But it always makes side CD be the longest side or so forth. So this one is made where it can't be broken into a non-quadrilateral, can't be non-simple, and it's also made in such a way that CD is always at least as long, if not longer, than AB. Okay, which is not restricting it, it's just a way of labeling it so that you label it with the longest side there. All right, so that's the isosceles trapezoid theorem. Here's the properties of the isosceles trapezoid. We can hide or show the diagonals and look at that. Okay, so isosceles trapezoids.